So hi everybody, welcome. Today I want to talk to you about dynamic restructuring of supported metal nanoparticles and its implications for structure-insensitive catalysis in this episode of Prototype Splash Talks. This is work that I started during my PhD at Utrecht University with my advisor Bert Weckhuizen. We traveled all over the world to perform experiments. We went to Oak Ridge National Laboratory to perform the Institutem that I'll be discussing, the Paul Scherrer Institute in Switzerland for the XAS measurements, and the work was sponsored by BASF and NWO, the Dutch Organization for Scientific Research. So before I dive into explaining what structure-insensitive catalysis is, catalysis is of course extremely important for the chemical industry. It's estimated that about a third of the global gross domestic product, or around $30 trillion every year, is directly affected by catalysis. It's important for our food production, but also more and more we're starting to see that it will play an imperative role in our environmental remediation. So of course, in order to design the better catalysts that we so drastically need, we need to understand how they work first. So structure insensitivity. It's an empirically observed phenomenon in catalysis where we take the turnover frequency, which is the surface normalized activity, the turnover of a catalyst normalized for the amount of active surface that's exposed, and we plot that against the nanoparticle size of the catalyst. So a lot of catalysts are supported metal nanoparticles. It's a big class of catalysts, for example, nickel nanoparticles on a silica support. And by changing the catalyst particle size and plotting their surface normalized activity from one another, we can see different trends for different types of reactions. So for some reactions, we see that there's a exponential increase in activity for smaller nanoparticle sizes. These are called sigma bond structure sensitivity. Sigma bonds are preferentially cleaved over very undercoordinated atoms, preferentially single atoms, and pi bonds are preferentially cleaved over atomic clusters of some degree of coordination. So those two can be quite well explained, but we also have this other class of structure sensitivity, which is structure insensitivity, reactions that show no difference in their turnover frequency with catalyst nanoparticle size. And this is a strange phenomenon, because we can explain, like I said, structure sensitivity. We know that if we test our catalyst particle sizes of different mean particle size and plot them against the turnover frequency, that we see a maximum for CO2 hydrogenation, for example, a maximum in the activity for a particle size of about 2 to 3 nanometer. And that means that the surface normalized activity, that the atoms that are exposed apparently don't all have the same activity in this specific catalytic reaction. And that's caused by different nanoparticle sizes having different exposed sites. Smaller nanoparticles will have much more defect sites, much more step and edge sites, and larger nanoparticles are believed to have many more flat terraces because they're just much larger. Aside from that, of course, when you make smaller nanoparticles, you're starting to have a certain degree of atomic-like behavior. You're starting to step away a little bit of metal D-band formation. So those two big effects, geometric effects based on the site geometry, and electronic effect based on, for example, how big the nanoparticles are, those explain a lot of our understanding of structure sensitivity. However, again, like I mentioned before, now that we can explain, or now that we know how to explain structure sensitivity, it makes even less sense that we observe structure insensitivity. And it's been said before, for example, by Norskov, that the absolute absence of any structural effects, both geometrical and electronic, is unexpected and no examples can be found, theoretically speaking. However, if we take what we empirically know to be a classical structure insensitive reaction, which is ethene hydrogenation, we do indeed observe it. We do indeed observe that some reactions have barely any or really no change in surface normalized activity with particle size. So here we see the CO2 hydrogenation example that we saw before, where we see a clear change in activity for different particle sizes. And here we see the surface normalized activity for ethene hydrogenation on the right, which barely changes. So we decided to examine this strange phenomenon with those two different reactions. We have a structure-sensitive reaction, CO2 hydrogenation, and a structure-insensitive reaction, ethene hydrogenation. And we tested our supported metal catalyst particles with all kinds of different techniques. One of them was using the protochips in situ high-resolution transmission electron microscopy cell, or we did high-resolution transmission electron microscopy with it, where we deposited nanoparticles onto the silicon nitride membranes via spark ablation, and then we took these, inserted them into the microscope, heated them first before we turned on the microscope to avoid any carbon deposition, heated the nanoparticles in hydrogen, so reduced our nanoparticles at up to 500 degrees. The nanoparticles reduced, then we started recording our images, and at that point we would decrease the temperature to about 150 degrees, flowed nitrogen, and then flowed either ethene or CO2. So here I'm just showing it for ethene because I can tell you that for CO2 we saw no significant change in our nanoparticles once we started flowing CO2. But for ethene we observed something very interesting. So flowing ethene over our nanoparticles, and we measured this over a whole range of different nanoparticles, we could see that the lattice fringes, if we did a fast Fourier transform on those areas, we could see that there was quite some expansion once we started flowing ethene. So there was a lattice expansion once we started flowing ethene, and then if we reduced again in hydrogen, we saw it contract again. And this was measured over, like I said, a whole range of different nanoparticles. And for CO2 hydrogenation, we really didn't see this effect. So lattice expansion under ethene of approximately 2% was observed over different areas of different nanoparticles. Interesting, of course, because this is a transmission technique. And that means that in any case, we're averaging out over this expansion over the entire nanoparticle. So even if it is only a surface expansion, technically speaking, let's say we would expect it to be more than just a surface expansion. So after doing these transmission electron microscopy experiments with the protochip cell, we knew that there was some effect of ethene and there was no effect of CO2 hydrogenation. So we wanted to look at in more detail. We did in situ X-ray absorption spectroscopy, quick XS actually. So we measured a spectrum. We had the resolution to measure a spectrum, time resolution, to measure a spectrum every 100 milliseconds. So again, we took our catalysts of different nanoparticle sizes and started to flow after reduction either ethene or CO2. And what we there saw was quite similar to what we observed in transmission electron microscopy, which was that we saw really a distortion in the geometry once we flowed ethene over our nanoparticular samples. And for CO2 hydrogenation, this effect was much, much less. If we did see a change in the X-ray absorption spectrum, it was mainly in the Zanes region, mainly in the region where we expect oxidation changes to occur. And for our ethene samples, we saw a large degree of really geometric restructuring. The XFs significantly changed. Then we pulsed our samples with hydrogen and ethene, hydrogen, ethene, hydrogen, ethene, and the same for CO2, even though you can't see these distinct features here at 4 angstroms. And these plots that you see here are fast Fourier transforms of our subspectra. That means that we're looking at more or less a radial distribution function. Let's look at it like this, at least. Meaning we're looking at the positioning of the scattering of the average absorbing atom. So at about 2 angstroms, we would expect our first nickel-nickel bond, and at 4 angstroms, we would expect the second shell to occur. So this means the fact that we're seeing something forming and going away that is happening repeatedly, that means that basically we are creating and taking away long-range structure or long-range second shell, but some sort of a periodic ordering is occurring and going away. And this sort of breathing of the nanoparticle is apparently reversible. So that was very, very interesting. We didn't expect this difference in the two different reactions to have all of these kinds of characteristics. We examined this a little bit farther by fitting for the Diavala factor in the XF's equation for these 70,000 spectra per experiment. And by plotting that against time, we were able to deduce a few important things. Firstly, that the reversibility of adsorbate-mediated surface restructuring decreases with particle size. Smaller particles restructure less. This peak we see structures less. Larger particles restructure faster. This peak is sharper. And there's always a degree of ethene-induced restructuring, which is irreversible, meaning the first peak is always the highest. So taking that, what we've now found, this counterintuitive restructuring that we're seeing for this structure-insensitive reaction brought us to an idea. What if actually the fact that our surface restructures because of this ethene, because of a very strongly absorbed intermediate on the ethene surface, what if that is what causes us to see structure insensitivity? If this surface absorbed intermediate exposes sites that are very similar on the nanoparticles, this could explain it quite well. So we tested that hypothesis by taking our structure sensitive reaction, CO2 hydrogenation, which you can see that the surface normalized activity changes for different catalyst particle sizes. We flowed ethene over those two different samples, and we removed the ethene. We flowed hydrogen and nitrogen, so that we were only left with this irreversibly absorbed intermediate on the surface. And we measured the activity of CO2 hydrogenation, and we could see that after this surface restructuring, the turnover frequency was nominally the same. So basically, we made our structure sensitive reaction structure insensitive by flowing ethene, and that really explained for us why we observe this straight line, why we even observe structure insensitivity, simply because our nanoparticle restructures because of ethene. And for CO2 hydrogenation, for the structure sensitive reaction, we see nothing of the sort. So with that, I would like to thank everybody who contributed to this work, especially Bert Weckhuizen, my former PhD advisor, Anatoly Frenkel, Ray, and Maarten, also Matteo and Florian, of course. And I'd like to thank you guys for watching this episode.